In this video, we're going to look at coupled reactions. So many biochemical reactions that are very important are not necessarily thermodynamically favorable. That means that they would not occur spontaneously under certain set of conditions, and that their delta G value would of course be positive because of that. However, these unfavorable chemical reactions can often be coupled or linked to a favorable spontaneous chemical reaction. Under those circumstances, the overall delta G for the coupled reaction is the sum of the delta G values for the individual steps. Now, of course, we know that ATP is the energy currency that's used, and it's often used to couple unfavorable reactions because it has a very negative delta G value when it's hydrolyzed. So let's look at an example to help us illustrate this. Let's look at the example where the molecule fructose 6-phosphate is phosphorylated, or we add a phosphate to it in order to produce fructose 1,6-bisphosphate. Now, the reason we're looking at this reaction is because it is a very important step in the biochemical pathway called glycolysis. And therefore, it is very important that this particular reaction occurs and we produce fructose 1,6-bisphosphate. If we're not able to produce this, then we cannot break down glucose and ultimately form energy, which is necessary for life, of course. Now, as you can see, the way this reaction is written, it is non-spontaneous. Under standard conditions, it has a very positive delta G value. However, instead of adding a phosphate to it, just an inorganic phosphate, it's possible to take a phosphate off of ATP. Remember, if we hydrolyze ATP, we produce ADP and a free phosphate. An enzyme can take that free phosphate and add it to our fructose 6-phosphate. So in other words, our phosphate here is not coming from inorganic phosphate, it can come from ATP. So therefore, we're coupling those two reactions together. And of course, the hydrolysis of ATP is very exergonic, negative 32.2 kilojoules per mole. So if we add these two reactions together, we would cross out anything that's opposite each other in the two reactions. Water would cancel out here. And if we add these two reactions together, we would get an overall reaction, and the overall reaction's delta G value would be the sum of the individual steps, as we said. So in other words, adding these two together, we get fructose 6-phosphate plus ATP yields fructose 1,6-bisphosphate plus ADP, and the delta G value under these standard conditions is the sum of these, and as you can see, it is very exergonic. So we're able to drive this non-spontaneous reaction in the forward direction, in the spontaneous direction, by coupling it with ATP hydrolysis. Now, looking at the delta G values, we can get a lot of information, but we also want to look at the equilibrium constants for these two reactions here. So we can convert our delta G values for here and here, these two reactions, we can convert those into equilibrium constants. If we remember our thermodynamics for this reaction, where A and B are my reactants, C and D are my products, we can calculate the equilibrium constant from the delta G value under standard conditions. So the delta G standard and the equilibrium constant, where the equilibrium constant is the concentration of products over reactants, is related by this equation. Now, if we're trying to solve for KEQ, we rearrange this and we get this equation here. Okay? So if you would, take the delta G values for these two reactions over here and convert those into equilibrium constants. If you would, pause the video, get out your calculator, and give that a try. So let's look at the equilibrium constant for this reaction that is not coupled to ATP hydrolysis. Of course, we have a positive delta G. If we plug that into our equilibrium constant formula, looks something like this, we should get a equilibrium constant of about 0.0014. So that means that if we put that over 1, that means for every 1 mole of our reactants, we have only a fraction, or 0.0014 moles, of our product. So that means that our equilibrium lies far to the left. So under standard conditions, at equilibrium, for this uncoupled reaction, we have a lot higher concentration of reactants and a very relatively low concentration of product. So we form very little product when this reaction is not coupled to ATP hydrolysis. And that's not a good thing if we need glycolysis to occur, which we often do. So how do we get that product to form under these when it's a non-spontaneous reaction? Well, of course, as we'll see in a minute, we can couple it to ATP hydrolysis. But before we do that, let's simplify this just a little bit. Let's kind of disregard the concentration or account for the concentration of phosphate, so we can just look at the concentration of the fructose 1,6-bisphosphate to fructose 6-phosphate. Okay, that way we can compare it to our coupled reaction maybe a little more directly. So here's our equilibrium constant that we just calculated, and under most cellular conditions, the concentration of our free phosphate, inorganic phosphate, is about 1 × 10⁻³ molar, 1 × 10⁻⁴ molar, somewhere in that range. So let's say that the concentration of our free phosphate here is about 1 × 10⁻³. So if we plug that in, then it's a simple matter to multiply both sides by 1 × 10⁻³, multiply that over here, and we would get 1.4 × 10⁻⁶ is equal to the concentration of fructose 1,6-bisphosphate to fructose 6-phosphate. So when we account for the cellular conditions of phosphate, it shows that our equilibrium lies even further to the left. So we produce almost no fructose 1,6-bisphosphate under these conditions. So now let's look at the coupled reaction, the reaction that is coupled to ATP hydrolysis, and you should have calculated your equilibrium constant for this exergonic reaction. So plug in those values. We get about 612 as our concentration, our ratio of products to reactants. Now again, that's a much, much higher ratio than what we saw for the uncoupled reaction. For every 1 mole of our reactants, we have about 612 moles of the product. So that tells us that under these conditions where we've coupled the reaction, we produce far, far more, much higher concentration of the product. Now again, to compare it directly to the other one, we just need the concentration of fructose 1,6-bisphosphate to fructose 6-phosphate. So here's the equilibrium constant we just calculated. And this isn't always the case, but let's just assume that the concentration of ADP and ATP are roughly equal. So under that condition, we could just cancel those if those are equal. And so our ratio of fructose 1,6-bisphosphate to fructose 6-phosphate, again, is still 612. So we can compare that now directly to what we saw for the uncoupled reaction. And that's what we're going to do here. For the coupled reaction, the ratio of the product to reactant, 612. The same product to reactant here, 1.4 × 10⁻⁶. You can see the huge difference, how this one lies incredibly far to the right in relation to this one, which lies incredibly far to the left. So if we could take the ratio of these two, divide 612 by 1.4 × 10⁻⁶, we get 4.4 × 10⁻⁸. So comparing the coupled to the uncoupled reaction tells us that our equilibrium ratio is about 4.4 × 10⁸. That's a huge number, times greater in the coupled versus non-coupled reaction. So we really, by coupling it, we shift that equilibrium way to the right, making that very, very spontaneous, producing a relatively high concentration of product when compared to the uncoupled reaction. Now, we often couple ATP with ATP hydrolysis with non-spontaneous reactions, but we also have to produce ATP. So how do we produce ATP? Well, one way is through metabolism. Uh, This is kind of surprising, I think. Resting humans turn over about 65 kilograms of ATP per day. So a kilogram's what, about 2.2 pounds. So that's well over 100 and close to 130 or so pounds of ATP per day. That is amazing. So here, the equation we're looking at here is an overall chemical equation for carbohydrate metabolism. Essentially, what we're looking at here is C6H12O6, that's glucose, reacting with oxygen, produces carbon dioxide and water, and we can also take ADP and phosphate and produce 32 ATPs. Now, I know that's probably not quite clear, so let's break it into two half reactions. Here we have our reaction showing glucose reacting with oxygen, gives us carbon dioxide and water. This reaction here is oxidation reduction reaction, and this breaking down glucose is very, very exergonic. A lot of free energy is released. Now, that free energy can be coupled to not the hydrolysis of ATP, but the production of ATP. So that free energy can drive the production of ATP and can be used to take ADP and phosphate and produce 32 ATP molecules. So 1 mole of glucose, we can produce 32 molecules or 32 moles of ATP. And then that ATP, of course, can be used in the cell to couple to other endergonic reactions, and that's why ATP can be used as the kind of the energy currency. So the phosphorylation of ADP to produce ATP, that would be very endergonic. Here you can see positive 1,600. And overall, if we add these two together, we get the overall delta G value, which is very, very negative. So we phosphorylate the ADP, and we still have a lot of free energy left over. And the reason for that is that it allows the ATP production, this free energy change, this large release of free energy, allows the ATP production under virtually any physiological conditions. Remember, these delta G values, when they're non-standard, they depend on concentrations and other cellular conditions. And so we can produce ATP through glycolysis under most cellular conditions because of how exergonic it is. So understand how coupled reactions work, how ATP can be used to couple two reactions, and then how those delta G values relate to equilibrium constants, and how those equilibrium constants can give us ideas about concentrations. And then, of course, we can, as we'll see later in our course, we can use metabolic pathways to produce ATP in very important chemical reactions.